Alright, welcome to video 11-4A. In previous videos we have talked about similar figures. We're specifically in this section 11-4, lesson 11-4, going to be focusing on similar triangles. And just like congruent triangles, we had some what we called shortcuts where we didn't need to know necessarily all the pairs of congruent sides and congruent angles in order to prove that the triangles were congruent. We have the same thing going on with this, you guys. We do not necessarily need to know all three pairs of congruent angles, and we do not necessarily need to know all three pairs of corresponding congruent sides in order to conclude similarity. There are certain combinations that are okay for us to know a piece of the puzzle and therefore be able to conclude the full picture, okay? So the first one is called angle-angle similarity. And I'm just going to star this box at the top of page 612, by the way, is where we are, because we're really not going to focus on the proving so much, so you can cross that word right out there, but we are going to focus on the fact that all we really need is two angles to be congruent, two pairs of angles to be congruent, and then we can conclude that the triangles are similar. And just intuitively, you guys, think through that with me really quickly. Looking at the diagrams that we have here in example 1, it says given that A is congruent to X and B is congruent to Y, so in other words, these two congruent angles here and here and here and here, are we able to conclude similarity? And I think you can see that because we know that our triangles are always going to add up to 180 degrees for all three angles put together in any one triangle, if two of them are the same, then that's going to force the third one to be the same automatically. So anytime we have three angles congruent, pairs of angles congruent, we can conclude similarity. So we're going to go ahead and just skip to the next page, page 613, and apply that next. So in example 2 here, we are applying the idea of angle-angle similarity, and we're trying to find missing side lengths or missing values of variables or whatever might be in the picture that we have in front of us. So if we look at example 2, we're being asked to find side BE, the length of side BE, which is missing from this diagram here, okay? What we can conclude, though, from the given information being, namely, that we see these parallel markings. Remember what that means is that we can have alternate interior angles be congruent. So angle C could be congruent to angle E, and angle A could be marked congruent to angle D. As soon as we know that, there's our two angles for angle-angle similarity. So it's important that we write a similarity statement just like we wrote a congruence statement, and that we pay attention to corresponding order for those vertices. Notice that the order is going to match whichever angles are marked congruent. So this goes A, B, C. So what is congruent to angle A in the big triangle on the right? A is marked congruent to D, so D is the first letter. B is a vertical angle pair, so it's an angle that is used on the left side and the right side triangle. That vertex is used in both. And then finally angle C is marked with just one tick mark, and the corresponding piece over in the right triangle is angle E. So notice that we want to make sure that this similarity statement is in corresponding order. And I'm not sure if we've mentioned this so far, but it's worth mentioning again. Remember, this symbol right here is a symbol for similarity. It's kind of like the congruent symbol, only the equal to part is taken out, and that's because we don't have equal sizes, we just have similar shapes, okay? So if we're going to find BE, we're going to need to, now that we've proven the triangles are similar, set up a proportion. And in order to do that, we have to figure out what sides correspond. We've got our little road map here, so we can set up the pieces that we need. BE is going to correspond to BC, the last two letters of each of those, so BE over BC on the right-hand proportion. And then BD and BA, we know, BD again coming from the right triangle in the numerator over the left triangle in the denominator. Keep our substituted pieces or substituted values in that order, and then we'll be all set. So we have 54 over 36 equals BE over 54. And what we need to figure out is to solve for BE. Now your book leads you to multiply both sides by 54, but remember we're going to work with the LCD. So let's go and do a little bit of work on finding the LCD here. Two denominators that are used are 36 and 54. So if we do prime factorization for 36, that is 4 times 9, as you know, but 4 is 2 squared to break it down into its smallest primes, times 3 squared is my 9, okay? 54 is 6 times 9. 6, though, is 2 times 3, and 9 is, as you know, 3 squared. So that's actually 2 times 3 threes, or 2 times 3 cubed. So if we put those two prime factorizations together to create an LCD, remember what we're doing is we're taking the highest power of any factor that's used. So obviously we're using a 2 and we're using a 3, but the question is to what power are we filling in for those? Well, that's going to be because the highest power of 2 that is used anywhere in these prime factorizations here is 2 squared. So we're going to use a 2 as a power on the 2. And then going back and looking at in this group of prime factorizations, what the highest power of the 3 that's used is, that's 3. So we're going to put the 3 as the exponent there. And so guys, that's actually 4 times 27, or 108. So in order to clear out all of the fractions in this proportion to solve for BE, what we want to do is just multiply by not 54, but by 108. And notice what will happen there is what happens in all of our algebraic examples when we multiply through both sides of the equation by the LCD. The 36 is able to cancel and leave a factor of 3 out of the 108, and the 54 is able to cancel with the 108 and leave a factor of 2. So we're looking at 2 times BE on the right hand side, and 54 times 3, or 162, 54 times the leftover 3 there is 162 on the left hand side. So 2BE equals 162, and therefore there's our BE equals 81. Okay, so now let's look at part B of this example. We're finding RT out of this diagram where we have overlapping triangles, and I know that we did this before in our Your Turn, so it's probably a good plan to do that again, to pull off the triangle diagrams so that you're not having them overlap, but that you're able to label common vertices. So we have R in the upper left hand corner of both, then we have S and V as the other two vertices of the small triangle, and we have T and U as the other two vertices of the large triangle. So what we're trying to figure out is, does RSV check out as similar to RTU here? Well, because we share an angle R in both the small and the large triangle, that's one pair of angles, and it's also given in the diagram here that angle S is congruent to angle T, and of course R is shared, so that's our reflexive property, as we've seen in other proofs before. So now how can we say that they are congruent? It's by the angle triangle similarity theorem, if we want to abbreviate that ever, as we're wrapping that up. Oh, and I should actually have 2 tick marks on that angle R, shouldn't I, you guys? Sorry, because we already have a single tick mark used in the diagram itself. There is, I think, a typo. I'm not sure if it's been changed in your version of the textbook, but this should say the same thing as it says in the top part of B here, which is that its RSV is similar to triangle RTU. So now that we've proven the triangles are similar, we're going to set up a proportion, and we're trying to figure out what RT is, so it makes sense that RT is a part of our proportion. Remember that we want to keep consistent numerators the same and consistent denominators the same. So it looks like RT and TU as the numerators are coming from the large triangle, and the denominators are coming from the small triangle. Stylus issues here, sorry. So large over small, okay? RT corresponds to what? If we look at our similarity statement at the top, that's our roadmap, just like our congruent statement was our roadmap for our proofs. And we can set up our proportion because RT corresponds to RS, and RS's length is 10, so we'll fill that in. TU is going to correspond to SV, and SV's length is 8, where TU's length is 12. So again, let's do some quick LCD work over here. The LCD of 10 and 8, where 10 factors down to primes of 2 times 5, and 8 factors down to 2 cubed, 2 times 2 times 2. When I merge those two together and get an LCD, I have a factor of 2 and I have a factor of 5, but the exponent that's used at the largest it's used on the 2 is the third power there. So that's actually 8 times 5, or 40 is my LCD of 10 and 8. So if I go ahead and introduce times 40 on both sides of my proportion here, what's going to happen is what always happens. All denominators are going to disappear with common factors in the LCD. So we're going to leave a factor of 5 out of the 40 on the right hand side, and a factor of 4 out of 40 on the left hand side. So writing an intermediate step over here, we're going to have 4 times RT is going to equal 12 times 5, or 60, or RT comes out to be 15. Moving on to our next slide, we have some your turns that I'd like for you guys to take a look at, and those are numbers 6 and 7. And again, redraw these diagrams, you guys, just like we did for that last example, part B of example 2, okay? Make sure that you separate the triangles that are overlapped, like in number 6, one on top of another, and in number 7, they're not overlapped, but it might make sense to just really quickly off to the side, you guys re-sketch. So there's my left-hand triangle. It probably makes sense to sketch that larger right-hand triangle, but to reorient it so that it can be easily seeing the corresponding pieces. And of course, number 6, we want to do top triangle and large triangle for similarity there. Okay? All right, we'll see you guys in the next video.